Yeah, so thanks to the organizers for inviting me, and yeah, it's a pleasure to be speaking here. And one of the organizers, Zheng Han, is one of the reasons why I'm very interested in 3D topological code. So if you don't like the talk, then blame him. Oh, and yeah, another thing I just want to reinforce, please feel free to interrupt me and ask questions during the talk. Okay, so the thing I'm going to talk about is this new family of codes we recently made up called layer codes. And the point of that, or let's say like the overview, is that they are the best possible codes you can have in three-dimensional space if you have local checks. We'll get to sort of definitions of all these things, but I will say this is an asymptotic statement. So we're living in sort of asymptotic land here, not small-scale practical land. Good. Yes? Oh, yeah. So sorry, I'm sort of saying 3D grids, so let's just focus on lattices that are going to be grids. So not like hyperbolic space. Periodic boundary conditions doesn't really, the boundary conditions don't really matter. It's the Euclidean space, whatever boundary conditions you want. Okay, and another nice thing you'll see is that these codes are relatively simple. They just come from coupling a bunch of surface codes together. So in some sense, they have some very 2D features as well, even though you need 3D to actually construct them. Good. And the plan for the talk is going to be, I'll go over some background, maybe at the speed people kind of need, because a lot of these things have already been covered in various talks today and this week. And then I'll tell you about the construction of our codes. And finally, the properties. And hopefully we'll get time to sketch like sort of the proofs, or at least say it in words, the idea of the proof. And the nice thing for me is I feel like all these ideas, the construction and also the properties, are pretty simple given you know a few key ingredients. Good. So let's start with background. So the kind of codes I'm going to talk about are all going to be these CSS codes. Kalderberg, Shaw, and Steen are the people this is named after. And these are kind of the simplest possible codes you can have, but they end up doing really well. Like we'll see here, you sort of can get the best possible codes in 3D from them. We have recently seen you get the best possible codes if you don't have any spatial restrictions, but have LDPC codes from these. So even though they're quite simple, they can really get you a long way. And I'm going to try and do everything by example. So this is like a general construction of a whole family of things, but I'm going to focus on pretty much one simple example. And so let me introduce that pretty slowly. So hopefully everyone, even if they're not an expert, can keep up, and feel free to ask questions if you're not an expert. Good, and hopefully the experts won't be too bored. Let me just establish some notation. I'm going to use this notation, the tanagraph. So here, these little circles are going to represent my qubits, some C2s. When they're put next to each other, that's a tensor product. These red squares are going to represent my Z checks. And so what this little picture represents is the repetition code. And maybe I should just write this for completeness. This is the tanagraph of the repetition code. So the checks here are ZZI and IZZ. Okay, everyone's good with this? And what you get from this is a code space where we're going to store our information, which is, okay, span of these two states that are +1 eigenspace, 0, 0, 0 on 3 qubits and 1, 1, 1, which is isomorphic to C2 again. And beyond these checks, the other class of operators we're going to be interested in are the logicals, which commute with all the checks but are not generated by them. So here, hopefully this is familiar. The logicals, which I denote like this. X is going to be flipping all spins, which you can check commutes with those checks, and Z, which I'll write like this. Any Z will commute with these checks, and a single Z or any odd number won't be generated by them. Good, so these form your logical Pauli algebra. I'll give you this qubit. Okay, but this code is not very good quantum code because a single Z operator can cause an error. So let's go to a slightly more complicated version, which uses this idea of concatenation that I'm going to rely on a bit more throughout the talk. And so hopefully this is pretty familiar to people again, but concatenation, the idea is you take now, say, 3 copies of this small code. So let me just draw the tangraphs. I'm going to kind of do increasingly less detail as we go along, so. Right, start by taking 3 of these and putting them next to each other. And then we're going to measure some, we're going to make a new code at the logical level. So we use the logicals on these different blocks. We have these X and Z logicals. And now we want to be able to catch Z errors, so we're going to put some X checks in. And hopefully, everyone sort of knows the story here. You make another version of the repetition code in the other basis at the concatenated level. So this tanagraph, the X part, and I'm going to use blue for X throughout the talk, is there just to catch Z errors. And it's essentially just another copy of the same code where instead of physical level checks, I have logical level checks. Cool. And with this code, the logicals you get are, so the checks are given by this, and the logicals, which might be important, so I'll write them down. Logicals, of course, X bar is given by, and I'll write the minimum distance 1, and then I everywhere else. And Z is given by, okay. Cool, so is this familiar to everyone? We're all good with this? This will be my main example, Shor's 9-qubit code. And now let me just introduce a bit more notation. So the way we talk about these codes, I think as we saw in the last talk, the most basic properties are summarized in these code parameters. N, K, and D, where N is the number of physical qubits, K is the number of encoded qubits or logical qubits, and D is the distance or the minimum weight logical operator. That's non-trivial. Cool. So for our first example, the repetition code, let's just write these down. This would be 3 physical qubits, 1 encoded qubit, and distance 1, because we had this weight 1 Z logical. For the 9-qubit code, we have 9 physical qubits, 1 encoded qubit, and distance 3, because those, and you just have to believe me, are the minimum weight logical operators. Okay, now we can kind of accelerate a bit. So hopefully if you aren't really used to codes, this all made sense. But I'm going to have to just sort of pull a few results out of the hat now that are sort of background, which I don't have time to explain in this talk. And the first point, which is very exciting, from a series of recent work done by started off by some people in this workshop that we heard about earlier in the day, is that good LDPC codes exist. And having this sort of CSS type of codes is already enough to get you these good LDPC codes. I didn't write codes. Okay, what does that mean? It means you have families of codes that have n physical qubits and sort of a number of logicals and distance that both scale with n. What does LDPC mean? Low density parity check. That just means when you write your tanagraph, it's essentially like a sparse graph with some constant degree everywhere. Cool. So this is great. If these sort of as good as possible asymptotic codes exist, what am I going to talk about? Well, we're going to think about this problem of being constrained by some physical dimension. So these codes exist, but unfortunately you can't realize them locally in any finite dimension. And this is because of this bound, which we saw in the last talk, which is called the BPT bound, Bravi-Palan-Terral. And I'm going to say, I'm going to be lazy about references here. Like all the references are in this paper, so references therein. And I'll try and attribute people just by name. But if you want a full list of references and links, just look in the paper, in the introduction. Everything's in there. Good. So Bravi-Palan-Terral bound tells us that there is some, if you're on like a Euclidean lattice in some fixed dimension, which I'm going to use as capital D, then your code parameters are restricted. So let's see if I can get this right. Capital D is like spatial dimension of your lattice. K and D are your code parameters. And this is assuming you have sort of a topological code. It's local in the spatial dimension. And it has sort of, local checks in the spatial dimension on your grid. Then this is bounded by ON. And it's sort of useful. So here we're going to imagine being on some grid. It's kind of useful to introduce this length scale, and we'll imagine it's kind of a homogeneous grid, so same length in all directions, at least same scaling. Then this n is going to be growing like this linear length L to the power D. So in 2 dimensions, if you have an L by L grid, you'll have like L squared scaling number of qubits, and similarly in higher dimensions. Good. And there are a couple of other versions related to this that I kind of like, that I think are a bit easier to think about for explaining where this sort of saturating these results come from. One is the Bravi-Terral bound, which is only telling you about the distance, again, of topological codes. And it tells you that the, sorry, I think I have this backwards. The distance is bounded by sort of codimension 1. So your logical operators can never sort of fill all of space. If you want to have a quantum code, they always have to be at least 1 dimension less than the spatial dimension. And then there's a nice bound by Ha, which I won't sort of say exactly what the assumptions are. Look for this nice paper in the references from our paper. But it tells you that the number of encoded qubits is basically bounded by codimension 2. So if you're in 2D, you can only have some constant number of encoded qubits. If you're in 3D, you can have sort of a line of encoded qubits. And I wanted to say a little bit about the intuition for this. Sorry, maybe I'm getting a bit low here. The intuition is, let me just draw a 2D picture. If you imagine you have your topological code, then if you take some kind of disk-like region, it's essentially correctable. You can just lose that whole thing, yeah.
Sorry, what is L here?
What is L? L is like the linear distance. So let me draw a little picture of like a 3D lattice. This is going to be like L by L by L. And D is your physical dimension. Okay.
Just for the Hobbound, is there an assumption about the distance growing or something?
Exactly. So I'm not like getting into it, but basically if you want to have like, for simplicity, you could imagine like optimal distance, but basically if you want to have a distance that's actually going to stretch across the lattice, that's where this comes in. Otherwise, you could just have as many bad qubits as you want. But essentially, let's say like macroscopically growing distance, the assumptions are actually, they're actually very loose in this paper, but they include something like this. Good. So the intuition for why these bounds hold, right, let's like draw this 2D picture, but you can do a higher dimensional version. You have this region that's kind of correctable. And so essentially you can just drop the whole thing and you still have your logical information. So that means you can support your logical operators outside this region. And by cutting out a big piece, you essentially make it codimension 1. So in this picture now, our logicals kind of live on this one-dimension-ish fattened boundary region. And so that's why you have this BT bound. The Ha bound is, in this case, if you want to have, as Noah said, like growing distance, essentially your logical operators have to be linear. And so then if you want to pack in these linear logical operators, you can only pack a constant number of them in because each pair takes up like a linear distance. you can kind of check that.
Another random question. Like the classical, the relative distance, the relative rate, we kind of know the right answer. Do we know that in the quantum case, like what the actual constants would need to be in the...
I'm not off the top of my head. Yeah, I think in this talk, it's all going to be like asymptotic. So those constant questions are actually very good. And, we should worry about them. But I haven't worried about them yet. Okay. Okay, so that was like a vague explanation for why these things hold. Now some examples. So the first example is surface code, which I'll introduce a little bit more carefully in a minute, but I'll just tell you the parameters. So in 2D, this kind of OG topological code actually already does the best you can possibly do, which is maybe one reason why it's still the best and most pursued kind of approach. Okay, so surface code is living on a grid. You have L squared kind of physical qubits. You encode a constant number of logical qubits. So I guess I should say order 1. Anyway, let's just say 1. And then you have a distance that's like linear. And you can't get any better scaling than that in 2D. This work is about a new class of examples. And amongst this class, there are families. So they live in 3D. And the main result is that you have, so you're in 3D, you have an L cubed kind of growing number of qubits in this sort of cube that this thing's going to live in. The number of encoded qubits is going to go like L, which is the best you can do. And the distance is going to go like L squared. I'm running out of space. And so this saturates, all these bounds. So asymptotically, it's the best you can do. And that's the main result. And then I just have to explain to you how that actually works. Okay, so maybe I'll kind of highlight that. Cool. So any questions about the sort of claim, or I can go through to the explanation?
You should maybe say whether that was previously achieved, or are there any other resultants you do?
Yeah, so there is a paper that appeared earlier in arXiv, which is why I made sure to put this up, which gets those parameters divided by polylog. But, essentially, we actually came up with this idea before this paper appeared, but didn't prove everything. And as far as I can tell, the relation's a bit unclear, although maybe we're converging to how they're exactly related, the two constructions. So there's related work that didn't quite.
Or thought-wise, 100% independent, right?
Yes,
But
they are completely independent.
Maybe after the fact that people will discover something like that.
Yeah, hopefully we'll establish exactly what the relation is. And yeah, I should say like the techniques used in this paper are totally different to the one that we use. And from my point of view, given my bias and my background, our construction is much simpler. But anyway, that's
But I
obviously.
should add a comment. That one just existence. This is a construction. It's very different. That's existent theorem. This is a construction.
And I'm going to show you the construction. Yeah, let's delete this board. Okay, so let's get into.
Before this, fractons didn't have the right distance.
Yeah. So that was like an open question, basically. That's in my open questions. You're going to see that this is not translation invariant. It is, in some sense, a fracton model, if you're familiar with that terminology. But why has no one found a translation invariant code that does that? I don't know. There's nothing saying it can't exist, so we're not smart enough yet. And maybe even amongst existing models, there is some family that would do that, but no one's proved that. Oh, yeah, sorry, I misinterpreted your question. Yeah, so in fractons, you can get L, but you can get L encoded, but you can't get L squared here. I mean, you can get L very easily here, which you'll see in a minute, without getting the distance. So it's all about the distance, really.
Now there's an open question to know what is number L something for fractal.
Cool. So surface code, I think we've seen it a couple of times this week. Let me introduce it again the way I need to talk about it, because we're going to and quickly abstract away from drawing all the lattice details, because it will just be impossible to keep track of. I'll have to refer to the paper for the lattice checks if you want those. But OK, one more time. Surface code is defined on a 2D grid. I'm going to put the qubits on the edges for this picture. Your checks are these vertex and plaquette checks. The basis I'm going to use is the original one, so x's around the vertex as the vertex check, and z's around the face as a face check. And then we build a grid with open boundary conditions. This is like the kind of boundary conditions I'm going to use of these qubits. Oh, actually, we need that much. Cool, so I have those checks and all the vertices and plaquettes, including these boundary ones, some truncated version. And then the logicals that commute with everything are strings. So Z strings on the lattice and X strings on the dual lattice. You can check will commute with all the stabilizers, but if they're sort of homologically non-trivial, like they cross the whole lattice and end on both boundaries, you can't generate them with the checks. So those will be our logicals. And they will be deformable if I multiply them with the checks. So they're kind of these strings that I can wiggle around. One other feature of this that I want to talk about is that if you have like a single Z operator in the bulk, you'll make some syndromes. You'll excite the surrounding vertex checks. And I'm going to call these E excitations, or E syndromes. And similarly, if you have an X somewhere, let's put it like maybe here, then it excites the surrounding plaquette checks and makes these syndromes I'm going to call M. And then the final thing, overloading my picture a little bit, is if I have one of these. So in the bulk of the surface code, if you're away from the boundaries, these always come in pairs. There's like a constraint that you can sort of prove locally. You can never make a single one of them alone. But if you're near the boundary, then the rules change. A single Z near one of these rough kind of boundaries can make a single E. So as opposed to in the bulk where you always come in pairs. And an X near one of the smooth boundaries can make a single M. Whereas in the bulk, it always makes a pair. OK. And so you could equivalently kind of call this, or condensed matter people would call this an E condensing boundary. In this sort of topological world, E condensing. In this topological world, condensing just means that you have some sort of defect or new rule that allows you to take some topological particle that can never be made alone and generate it locally. That's what condensation means in this context. This is the fancy word for that. And over here in the smooth boundary, you could call it M condensing. OK, so that just means you can make single E's near the E condensing, single M's near the M condensing, whereas in the bulk, you can't do that.
Yes, is there those letters coincide with the fusion rules we saw yesterday?
Not a coincidence, I guess.
If it's not a coincidence, you should really say.
Sure. I'm gonna abstract to this sort of anion theory in a second. So let me leave the lattice. So we're going to talk about like surface codes of all different sizes and fusing them together and doing all this sort of complicated stuff. You can still do it on the lattice, but it becomes just a lot of work to write everything down, and I don't have time to do that. So I'm going to sort of abstract everything to this higher level picture where we just keep track of a coarser sort of geometry. So I'm going to take this grid and just draw it as like a box. Then the important thing to specify is what the boundary types are. So I'm always going to put E condensing boundaries on the bottom and top, and M condensing boundaries on the sides. And then my pictures over here are going to look something like this. I can have sort of M string operator running across. I can have a Z string operator running down. In the bulk, if I have a finite piece, it'll make these E excitations. If I have a finite piece of M, it'll make M excitations. Sorry, a finite string of X's, it'll make M excitations. And then I can condense single ones of these into the boundaries if they are the right type. Okay, and yes, if you take an E and make another E nearby, there's a local operator that will fuse those two to the vacuum. So you can just join them by a piece of string and be left with no excitation. And this is called fusion. So in this theory, you get like a Z2 times Z2 fusion rule because E and M are independent and each one fuses with itself to the vacuum. So yeah, maybe I should write this anion theory. Here is, I think we saw this the other day, generated by 1 EM and F. And the fusion rules are Z2 times Z2. One is just the vacuum, which means like no excitation. Okay, and the braiding is basically that if you wind an E around an M or cross the string operators, then you pick up a -1, which just comes from the X and Z anti-commutation. Okay, good. And I want to fix some directions here that I'm going to stick to for the rest of the talk. I'm always going to have the X logical operators running in the X direction of my lattice, and the Z logical operators running in the Z direction. Good. And now the idea for our construction is pretty simple. We just want to draw this here. The idea is that if we take a stack of surface codes in 3D, we're going to get something with parameters. So maybe let me draw this. And I'll just draw it for this example. Obviously, this is this kind of single example is not going to give you these families you want. But I think the picture is sort of illustrative instead of drawing a really abstract picture. So let's draw. Imagine we have like a stack of these surface codes in 3D. If you consider these kinds of codes, they can get you something like L encoded qubits with distance L. So you kind of have L layers, and they're sort of L by L size. You get code parameters L cubed, L, L. So the distance is already, the number of encoded qubits is already good there. You just need to fix the distance. That's the idea. And how would you do that? Well, the basic idea is that if you concatenate this stack with a good code, so maybe I should say stack, then you would keep the scaling of the number of encoded qubits, but you would boost this distance from L to L squared. Okay, so let me just draw a little picture of that for this example. Yeah, so now you're going to have these like concatenated logicals, which just means you have new checks, which are products of like the logicals that were there before. Sorry. Okay, and the X ones. Okay, but you probably already sort of notice a problem here. Maybe someone can tell me what the problem is with concatenating a good code with surface code. The problem is these checks are now like totally non-local. So you have these products of string operators across multiple layers. And if there's an arbitrary good code here, it's going to kind of couple stuff from like one end right to the other end. It's going to be non-local and high weight. And so the whole game is then to fix this, which goes by the name like a weight reduction. So essentially, you need to take these really high weight checks and turn them into local low weight checks, but still infer these high weight checks. But once you kind of get this idea in your head, you're like, I just need to implement this locally, and I'm going to get my good parameters, and then I win. So if I get this, I kind of win.
So Doc,
Yeah.
if that's all you need to do, why you cannot using Hastings reduction of weight?
Yeah, I'm not sure if it's possible that one does the job Yeah. But I think that one's maybe more general than what I need to do. Cool. So, yeah, then we just need basically like one trick, and we can do this whole weight reduction. And the trick is to basically use this lattice surgery or some generalized version of it, which is essentially the same as topological defects. Cool. And so let's do a little example from over here. Imagine I had like 2 surface code layers, and I just want to implement this check that's like ZZ. The problem is, yeah, let's say, imagine these could be very far apart, and also that these Zs are very high weight, like weight L. But luckily, from sort of topological things, we know that you can locally implement this by just making a kind of defect along a line. So yeah, maybe I should say here, if you kind of have layer 1, this logical operator here corresponds to the E anion in layer 1, and this one to the E anion in layer 2. And so what you want to do here is essentially have ZZ become a symmetry. You can locally enforce that by making this domain wall condense, so locally disappear, E1 times E2. And okay, so that's your goal, to basically condense E1 and E2. That's not quite enough information to specify these domain walls. So to specify them, we do this thing called the folding trick, which essentially we take this 1D domain wall, we fold everything onto one side. So let me draw that. So now I'm going to have 4 half pieces of surface code joining this defect. It's like one-dimensional there. And to specify these defects of like, say, 4 copies of surface code, you just need to specify 4 independent anions that are all bosonic and braid trivially with each other. So in our surface code example, we already kind of saw this in a simple case where we picked E or M to specify a boundary. And there was 1 copy of surface code, so 1 anion was enough. We can't pick the fermion in this case with spin models because it is not a boson. And over here, what we want to do is pick now 4 independent anions, including this sort of E1. Well, what we need to do is have 4 things. So let's call these like layer 1A and 1B, 2A and 2B, coming from the 2 halves of layer 1 and layer 2. And we want essentially E1A, E2A to condense. We can also do it from the other side, so E1B, E2B to condense. You can still take a E anion and pass it through this check, because a Z operator will commute with this product of Z operators. Let me draw it on this side. So like an E1 anion can just pass right through, which in this picture corresponds to E1A, E1B condensing. So if this pair condenses, it's the same thing as saying E1A can turn into E1B, which is passing through in the unfolded picture. And then to complete this, if we put any other E's in, it actually decouples the whole thing and it becomes trivial. So we need to put some M's in, and there's only one choice that works, basically. So here, if you want this to be non-trivial, to not totally decouple, you then have to put in the product of all M's. Okay, and now once you've decided that these things condense, you've fully specified your one-dimensional defect. And if I kind of unwrap that, or unfold that back up here, it just tells you what can happen near the defect. So near this defect line, I'm allowed to have E from the bottom and the top layer coming in and condensing. I can have that from the other side too. I can have E passing through. And I can also have this like product of M on both top and bottom passing through at the same time. Okay, so that's what can happen at the defect.
I just have a quite confused. So previously you were describing the problem as, you know, if I want to do the concatenation, or into the issue of how exactly do I implement these like very long range, very like non-local in any dimensional checks. And so the particular example here is that I have two surface code patches and I'm trying to do a joint measurement of the two Z operators, right? And what is the exact proposal here in the QEC language?
Yeah, so that is what I didn't quite get to. So this is describing a one-dimensional defect in this high-level picture. But you have a recipe to turn any of these things into a local set of checks on the lattice.
Okay.
So like this, any of these one-dimensional defects, you can just take and convert into local checks on the lattice. There's a recipe.
I have a question. This defect, is that some kind of code version of gluing things together?
Yeah, it exactly glues.
If you want to glue them together with some topological operation, and
Yes.
this is the way to maintain somehow codes, right?
Yeah, so when you put the defect in between the layers, they're no longer like decoupled. They are forced to have some relationship between the anions in one layer and the other. So it definitely glues them together. Okay. Yeah, but there's one thing that the problem with this is it doesn't quite deal with the long range property. It will have some local coupling along the defect, but if you make them very far apart, it's still going to couple a long way. So you need one more trick, which I'll write here, which is the basically you. Yes. Okay. I'll move it after this one.
I have a quick question about this defect to local track prescription. When one applies that, how do the track weights behave locally then?
Yeah, it depends on the model, but we're doing surface code. They end up being like weight 6 or less. Local checks, weight less than or equal to 6.
So if I assume, if you multiply the 3 boson by M, you get a pair of fermions, does that change the weight? Well, I assume you can multiply each pair of E by the M, 4M.
Oh yeah. I mean,
You get 3 pair of fermions.
you could pick worse weights. I could say you can achieve this weight. There is obviously some choices you make to like make the best possible choice. Okay, good. So the final thing you need to do to fix this is to stretch out the defect, basically. So imagine these are really very far apart. Essentially what you do is just add in an extra layer of surface code into which these E anions can travel and the M anions. So this is now also a layer of surface code. And now we have these two trivalent junctions. So it's like the simple idea that occurs all over the place where you want to split up like a higher level vertex into trivalent vertices. That's essentially what we're doing with this junction. And now I just need to describe to you what is going on here that will implement this. Okay, and it is, again, pretty simple. It's just the defect that allows you to condense an E from this layer into this red layer. You're also allowed to pass a single E through. Okay. So if you have an E in this top layer, it can pass through the defect. And then you complete this with M, so it doesn't end up being totally trivial. It's using blue for M. And to be consistent with these two E condensations, when an M passes through, it has to spit out an M into this layer. So you have these three condensations. I mean, you could fold them into a boundary picture, and there would just be three condensations, similar to this one over here, but with one less layer. And if you take two of these and just kind of put them at either end of a surface code, you can check they exactly implement this. But now, because we have this surface code running between the two defects, we know that the defects themselves can be made local. This surface code we can turn into local checks, so the whole thing is like local. But it introduces some qubit overhead because you need to put a bunch of qubits in to this patch here. But it doesn't change the scaling, essentially. It just gives you a multiplicative constant factor. Okay, I want to introduce a little bit of notation to describe this a bit more simply. So this was just 2. What about when we have more complicated stuff going on? I'm going to go to this kind of like side view. So really along the defect, like it's very homogeneous, like nothing's really happening in this direction yet. So I want to just abstract that and draw this picture if you just sort of look from above. And this defect, I'm going to denote like a delta, or a dot, sorry. And it has the property that basically an E in some layer, which I'm looking at from above, so just a line, can just hop through this dot. And then the final property is that M on all inputs is allowed to disappear. So there's like a set of equations that define the defect. I'm just rewriting this without the extra dimension. And then it's natural to also define a similar defect where you just swap the role of E and M because they're equivalent in this theory. And I'm going to draw that one like a plus. So there's a similar defect, which I haven't used yet, but I'm going to use in a second. That I'm going to denote plus. And that one has the flipped set of rules. So wherever an E happened up here, M happens down here. Because they are interchangeable, this will also be kind of consistent. OK. Good. Now I can say what happens if you have a general Z or X defect. Now this would be a good place to write it. Okay, so essentially now I have all the ingredients I need to make the construction at a high level. I just need to tell you the recipe. Okay, so now imagine I have something like many layers involved in a check, and they could be very far apart. Well, my colors. Then I'm going to just need one new ingredient, which is that the endpoints of this check. So imagine this check kind of runs all the way through, hits these layers. Maybe it skips some layers in between, but it connects these ones. The defects I put in at these endpoints are just these ones that I introduced already. But in the middle, I put something different. So this one's like 4-valent, if you like. So there's some box here. I don't know what it is yet. And it's 4-valent. And it should have the rules that essentially like and E is allowed to enter this like red layer from the white layer. E is also allowed to pass through. And what I want is that if an M passes through this, it causes some syndrome. But the syndrome is like only recorded on the layer as a whole, so M should be able to pass through in the red layer. So there's some set of constraints I need to satisfy to make this represent a Z check. And the solution to those that allow the right motion is given by just combining these two tensors over there. Let me try and draw this correctly. So it's a plus tensor in this direction, because if I have an M excitation on this red layer, it's representing a syndrome, but the syndrome information just lives across the whole check. It's not localized to one part of the check. So I need to have basically this plus in this direction so the M's allowed to go through, if you look at the rules over there. And then I need to say what happens in this direction. And because E has to pass through in that direction, I'm essentially forced to put in this dot. So this allows E's to go through that way. It also allows E's to pass through into the red wall. And so that's the choice of the defects you put along the middle. So if there's many of them, you just make the same choice. And the ends are this slightly different choice. And that's the recipe. Very similar for X defects, so let me quickly write that.
And that replaces whenever the middle layer would hit the left beam.
Yeah, so what,
Right? Or only the bottom.
every time you're in the middle of one of these checks, you do one of these. And it's possible these defects just skip layers. It's determined by where the Z checks hit.
And it just, yeah.
Exactly. So if it skips it, it just goes through it, nothing happens. Kind of. All right, nearly to the construction. So let me just say quickly, you can probably already guess though, if I flip the basis and think about some X checks, I'm gonna have some picture kind of like this. And I basically just need to exchange the roles of the plus and the dot because they're equivalent if I switch E with M. And the blue strings essentially are the M versions of all these red strings were for E's. So the domain walls are described by this. Okay, and once you have that information, you have everything you need to go in and even make a lattice model of these defects between the blue and white layers and the red and white layers. But there's one slight ingredient missing. Because this is all embedded in 3D, when I have both red and blue checks, both X and Z checks, they will also intersect with each other. And you could ask, what do I put there? And if I make the simple choice of just letting them pass through each other, which is the first thing we tried, and we thought that worked for a minute, but it turns out that doesn't work. I can quickly explain why that is. If you just let them sort of trivially pass through each other, the problem is that you really want these like blue walls, say, which are like the X checks, you want them to block Z string operators, E string operators, because if they don't block them, they're not doing their job as checks. Checks kind of block you from putting down whatever operator you want without causing any syndrome. And when you have, so let me draw this little picture. When you have the red wall, like we saw before, the E excitation can like go into the red wall like this. And so if the red wall doesn't talk to the blue wall and the E excitation can go into the red wall, it can like go up to a blue wall, go into the red one, go past the blue one, come back into the white one and keep going, which is really what you do not want to happen because it means the whole thing's sort of broken and not correctly implementing the concatenation. Okay, so our question is like, what's here? What is that? And I've just sort of quickly sketched that if you pick the trivial crossing where they don't talk to each other, the whole thing breaks. And you can kind of pretty quickly check that you can find logical operators of weight L if you don't put anything there. Okay, and to solve this, you need a tiny bit more structure. So let me draw it on my picture over here. You need to go and take, so these crossings are corresponding to the intersections of the Z and the X checks. So everywhere that a pair of X and Z check intersect, you need to take the set on which they intersect and pair them up. So in this shortcode example, it's quite simple intersections. Each red just intersects with the blue on 2 spins. And so then for each intersection, you need to put this pairing, which I'm going to draw with a green line. And you know the number of qubits in the intersection has to be even because the X's and Z's have to commute by definition. So you can always find such a pairing. And we've sort of labeled the qubits 1 through n to lay them out on the line. So we just basically pair them up in order. That's the solution. So now we have this slight bit of extra structure. And this gives us 2 versions of this this kind of crossing. One version where there is no green line, and one version where there is a green line. And on the one with no green line, you actually do just put this trivial crossing. Those don't talk to each other. But when you do have a green line, you put something different. And what you really wanted to do is basically block E's from going this way and block M's from going that way. Because if you don't do that, you've sort of failed. And that forces you into this choice, essentially. So if an E tries to go through this guy, he spits out more excitations into the other part, which records that it's gone through. And if an M tries to go through that way, it spits out more excitations into this part, which records that it's gone through correctly. And so that's the choice. So I guess this one I could sort of draw as just nothing happens. They just trivially cross. Good. And with that, I can show you the one I prepared earlier, the full defect network for Shor's code. OK, so there it is, my attempt at drawing it. It looks better in tech, but this is hopefully passable. You have one layer of surface code for each data qubit. You have another layer of surface code for each Z check, and they're in a different direction. You have another layer of surface code for each X check in the other direction. And then you put in these sort of green lines where you have the pairing. And on those green lines, you use the defects. Well, you can't see it now because I just covered it. You use that defect with the plus joined to the dot. On these blue lines intersecting the white ones, you use those defects shown over there. On the red-white intersections, you use the defects also shown on that board. And that specifies the whole thing. There's also a slight subtlety that you need to do these resolutions. So for example, here, there is like this point where a bunch of defects come and meet each other at a point. Luckily, that's actually quite an easier problem. So you essentially get like some finite, if you want to think about it on the lattice model, you get some finite number of edges that's all kind of meeting at a point. You just find the stabilizers there that gap everything out. Sorry, the maximal commuting set. So you have to solve a bunch of these small point problems too, which I won't go through, but those are essentially just some finite problem you can actually solve by hand very easily. And yeah, with that all specified, you can even go and write this down as a lattice model. As a lattice set of checks. So that's in the paper. And because of all these little cases, there are a bunch of different types of checks. But, so yeah, I should say this. Recipe to make lattice checks of weight 6 or less, which is kind of nice. So if you can't read that, I'm just writing that you can find some procedure that sort of automatically takes any of these codes you've stuck in, produces this defect network, and then you make your lattice model, your lattice set of checks that live on this sort of cubic lattice, and the check weight ends up being maximum 6, and that's like for whatever you put in. It really doesn't matter what you put in. You can even put in non-LDPC codes, and you'll still produce checks of weight 6 by this thing. So where do the good LDPC codes come in? It turns out that this construction, actually when you go through the details, really realizes these parameters. And it's actually there it becomes important that the thing you put in is LDPC. So how much time do I have? Like 5 minutes? Or I'm over? Yeah, okay, that's good. So let me just tell you.
You're on your last page in the emotes.
I think I actually don't need to even write anything more. Just tell you that the code parameters you achieve from this, if you put in a good input, good LDPC code, then you achieve these parameters. And ask me in the coffee break how the proofs go. Thanks.